June 19, 1944. The wind over the English Channel roared like a living thing. For 3 days, a violent storm had battered the Normandy coast, tearing ships from their anchors and smashing steel into the waves. The great Allied invasion that had begun just 2 weeks earlier now hung by a thread. At Omaha Beach, the American harbor, WWII, was gone, broken apart by wind and water. Giant concrete blocks that once formed the floating piers were scattered like children's toys. The bridge that had carried tanks and supplies from sea to shore had vanished beneath the churning gray water. But 20 miles east, near the small French town of Arromanches, the British harbor, WWII, was still standing. Against every law of nature, it had survived. Waves crashed, wind howled, steel twisted, but the bridge refused to break. When the storm finally eased, Captain Thomas Blake of the Royal Engineers walked across the trembling planks, staring at what was left. Steel bolts had cracked. Iron chains had snapped. Yet something simple, something handmade, still held everything together. The ropes. They were thick, dark, and rough, soaked in linseed oil and tar. They stretched between the floating roadways like veins, alive, breathing with the motion of the sea. Blake whispered to himself, "It's the ropes. They held." And in that moment, he remembered an old man from Dorset, a farmer with hands stained by tar and years of work, who had taught the army how to make rope that could flex with the ocean instead of fighting against it. Months earlier, that idea had been dismissed as foolish, a relic of another century. But on this storm-torn morning, when machines of steel had failed and millions of lives depended on what remained, it was the farmer's homemade rope that saved the longest bridge of the war. The knowledge of a man who had never left his fields had helped hold together the greatest invasion in human history. The problem no engineer could solve. In 1943, as Allied commanders planned the invasion of Nazi-occupied France, one question kept coming back with no answer. How do you land an entire army without a port? The ports of northern France, Le Havre, Cherbourg, Calais, were either too far, too heavily defended, or rigged with explosives by the Germans. Eisenhower's planners knew the truth. If they couldn't bring supplies ashore fast enough, the invasion would collapse. The solution was bold, almost impossible. What if they built the ports in England, then floated them across the Channel after D-Day? That idea became Mulberry Harbors, 2 giant artificial ports codenamed WWII and WWII, made of massive concrete blocks called Phoenix caissons, floating piers nicknamed whales, and roads stretching over 6 kilometers from ship to shore. They would carry over 9,000 tons of supplies each day: fuel, ammunition, tanks, medicine, food. Without them, there would be no way to sustain the fight. But as soon as construction began, engineers ran into a problem no blueprint could solve: the ocean. It was not just about building strong structures. It was about building flexible ones, structures that could move with the waves without tearing themselves apart. The floating bridges needed to bend, absorb shock, stretch, and recover. Steel cables were the obvious answer, but the sea said no. Every time engineers tested steel hawsers to connect bridge sections, they failed. Some corroded in days, others snapped under sudden strain. Even the strongest anchors couldn't hold the bridges steady once the water surged. The sea would not be tamed by force. In frustration, Royal Engineer officers tried every available design: metal chains, rubber joints, spring-loaded rods. Nothing lasted, and time was running out, and failure meant abandoning the invasion. Then, during a late-night strategy session at a naval yard near Portsmouth, a young officer, Lieutenant Charles Houghton, made an offhand remark. He recalled the old rope makers in his hometown of Dorset. Farmers who still twisted their own hawsers for fishing boats using hemp soaked in linseed oil and sealed with tar. He laughed when he said it. No one else did, because they had tried everything modern, and nothing had worked. So with nothing left to lose, they sent for a man who had never seen a battlefield, never held a commission, and never built anything bigger than a barn. An old farmer, a rope maker, and as it turned out, the missing piece in one of the most ambitious engineering feats in military history. The farmer from Dorset. In February of 1944, with only 4 months left before the invasion, a truck arrived at the Royal Navy dockyard in Portsmouth. Inside sat an old man in a wool coat, his boots muddy from the fields, and a coil of rope slung over one shoulder. His name was Arthur Perring, a 70-year-old farmer from Dorset who had spent his entire life working land, mending fences, and making rope for the local fishing villages. He had never seen a warship up close, never set foot in a military facility. But now, surrounded by officers and engineers, he was asked to do something that no one else could: teach the British Army how to make rope that could survive the fury of the sea. Captain Thomas Blake, a Royal Engineer in his early 30s, led the demonstration. He had a clipboard in one hand, skepticism in the other. "We're building a floating harbor for tanks," he muttered to a colleague, "not tying up horses." Perring didn't argue. He asked only for space and silence. Then he opened his bag and laid out bundles of hemp, manila, and jute fibers, freshly cut, smelling of earth and oil. With practiced hands, he began to twist them, 3 strands at a time, wrapping one direction, then countering it with the next, forming a triple-layered braid. He dipped each segment into a bucket of linseed oil and pine tar, sealing the fibers, then began coiling it slowly, tightly, like winding muscle. He didn't speak much, but he said one thing that made Captain Blake stop writing. "Steel resists the sea. This listens to it." The room went quiet. The engineers examined the rope. It felt soft, but strong. It stretched slightly when pulled, then returned to shape. When soaked in seawater for 12 hours, it didn't fray, didn't rot, didn't snap. Skepticism turned to curiosity. Curiosity turned to action. Within a week, the rope was tested on a floating pontoon. The trial was simple: moor it in open water, simulate wave conditions, and compare it to standard steel cable. The results were not even close. The steel cable snapped after 4 hours. Perring's rope lasted 22 and didn't break. It stretched, swayed, and recovered. Captain Blake wrote in his journal that night, "We scoffed at a farmer, but his rope outlived every bolt, chain, and wire we tested. It bends, it breathes, and it holds." By March, an order was placed for 10,000 meters of Perring's rope. Not from factories, from rope walks, long sheds where men and women twisted natural fibers by hand. The Navy called them secondary moorings. The engineers called them shock absorbers. But among the crews who loaded the reels onto transport ships bound for Normandy, they had another name: the Old Man's Line. And soon it would carry the weight of an army. How rope outsmarted steel. At first glance, it seemed absurd. How could rope, something made by hand in a barn, outperform steel cable forged in military factories? The answer wasn't brute strength, it was behavior. Steel is strong, but it's also stubborn. It does not bend easily. When a wave pulls on a floating bridge, steel absorbs that force all at once. It stretches a little, then hits its limit, snaps like a violin string. And when it fails completely. Rope, the kind Arthur Perring made, was something else entirely. It moved with the sea. It didn't resist the wave. It danced with it. That made all the difference. Each rope began with manila hemp, imported from the Philippines, chosen for its unique balance of strength and softness. The fibers were long and naturally water-resistant, ideal for absorbing force without fraying. When twisted into 3 opposing strands, each pull from the sea was distributed across the rope's spiral, like stretching a spring instead of pulling on a rod. Then came the treatment. First, Paring soaked the rope in linseed oil. It penetrated deep into the fibers, preserving their flexibility while sealing out moisture. Next, he brushed on a thick coat of pine tar, the same substance once used on the sails and rigging of British warships from Nelson's time. The tar hardened slightly when dry, forming a protective skin that resisted salt, sand, and rot. The result wasn't pretty. These ropes were dark, heavy, and sticky to the touch. But when engineers ran stress tests at the Royal Navy's experimental tank in Haslar, the results left them speechless. Paring's rope could absorb up to 20% elongation under load, meaning it could stretch to 20% longer than its resting length and still return to shape. Under extreme dynamic force, say a sudden jerk from a 10-foot wave, it held steady while steel shattered. More surprising still was its performance under constant movement. Over a 12-hour cycle, steel cables showed fatigue fractures, tiny hairline breaks that signaled failure. Paring's rope showed none. It wasn't just durable, it was alive in the mechanical sense. It responded to the sea, flexed with its rhythm, and survived by cooperating instead of resisting. A study by naval engineers concluded that Paring's triple braid construction, when treated with oil and tar, produced a mooring line with superior longevity, greater elasticity, and equal load capacity to galvanized wire ropes of the same thickness, with one key advantage: it did not corrode in salt water. Even better, it was quiet. Steel groaned and pinged under pressure. Rope made no sound. For ships and floating bridges that needed to operate under cover of darkness or evade enemy detection, silence was survival. Soon, the rope was no longer seen as a novelty. It became standard issue across Mulberry construction. Massive reels, each holding hundreds of meters of triple-treated hawser, were loaded onto Liberty ships bound for Normandy. The rope was used to connect floating piers to caissons, to secure bridges to the seabed, and to bind anchor points between pontoons like the sinews of a living structure. Even the American engineers, initially skeptical, began placing orders. At the request of General Leslie McNair, a batch of Paring's rope was tested at a U.S. Navy facility in Boston. The report came back simple: superior shock absorption under wave-driven tension. Recommend inclusion for cross-channel bridge mooring. By mid-April, dozens of British rope walks were producing nothing but Paring-style hawsers. At Chatham Dockyard, rope walks that once made rigging for sailing ships were reopened after decades of silence. Workers, many of them women and elderly men, stood for hours twisting fibers, dipping, drying, coiling. It was tedious work, dirty, hot, slow, but it was also critical. Each meter of rope was marked with a colored thread, indicating the week and location of manufacture. Quality control was strict. If the twist was uneven or the treatment incomplete, the entire coil was rejected. In war, even rope had to meet military precision. Captain Blake returned to Dorset once more before D-Day. He visited Arthur Paring in his barn and handed him a telegram. It read, "First batch delivered. Holding steady in wave test. Thank you." The old man barely looked up from his work. He was already twisting another line. "You don't fight the sea," he said, as if repeating an old family truth. "You ride it." That philosophy, the quiet wisdom of a man who had never worn a uniform, now flowed through every section of the Allied invasion harbor. It wasn't just a rope. It was a principle. And on the beaches of France, that principle would soon be tested in the most violent sea the war had ever seen. The system behind the rope. Britain, by early 1944, had become a nation of factories. From Liverpool to Leeds, every shop, yard, and warehouse had been pressed into the service of war. Ships, bombs, tanks, and trucks rolled off assembly lines with machine precision. But Arthur Perring's rope, his homemade trick, couldn't be mass-produced on conveyor belts. It needed something older, slower, and deeply human. It needed rope walks. Long, narrow buildings, some over 600 feet in length, where workers walked backward for hours, twisting strands of natural fiber into perfect, even tension. These rope walks had once served the Royal Navy in the age of sails, making rigging for ships like HMS Victory. Many had stood silent since the late 1800s. But now, under the pressure of total war, they were awakened once more. Across Britain, 22 rope walks were reopened, manned by a mix of retired sailors, village craftsmen, and women from the Women's Land Army. Their mission was simple, but vital: produce the strongest mooring rope in the world, and do it fast. Each facility followed the same specifications, now codified as Perring Pattern Type B hawser, 3-strand reverse twist, double treated with boiled linseed oil and pine tar, tension rated to 15 tons. The materials were natural but heavily standardized. Hemp and manila were imported in bulk through convoys from India and the Philippines. Treatment barrels came pre-blended, sealed in steel drums marked with military tags. But the technique, the twist, the pressure, the timing, couldn't be mechanized. It relied on touch, on sound, on feel. Workers learned to listen for the groan of an uneven strand. They learned that the rope should resist just slightly under the hand, like a breathing animal. It wasn't just rope making. It was rope craft, a form of knowledge passed hand to hand, person to person, without blueprints. At the Chatham Dockyard, one of the largest rope walks in England, Captain Thomas Blake watched rows of workers twisting and sealing ropes longer than a city block. He later wrote in his report, "This is not industry in the modern sense. It is coordination of ancient skill with military need. The farmer's method has become part of the war machine." Even school children joined in. In Dorset and Cornwall, high school girls were trained to spin smaller cords used to tie down canvas and netting for the mulberry harbors. Pensioners in Hampshire worked part-time sealing coil ends with wax and tar. The entire nation bent toward the task. Not because anyone saw glory in it, but because it mattered. Meanwhile, engineers redesigned the Mulberry Harbor anchoring system around the rope itself. Originally, the design had depended heavily on steel cables, steel shackles, and steel-driven anchors, all prone to rust, shock failure, or weight constraints. Now, the team at the Royal Corps of Engineers issued updated guidelines. Use rope hawsers in all dynamic connection points. Allow minimum 20% stretch tolerance in mooring points. Include slack adjustment loops every 30 meters to prevent overtension. At sea trials off Selsey Bill, a full-scale floating pier was connected entirely using Perring rope. It held through simulated storm swells. Observers noted that the structure moved more fluidly, distributed strain better, and, most importantly, recovered faster after each impact. From the outside, it didn't look like much had changed. But inside every joint, every mooring, every bridge support of the Mulberry Harbors, thousands of meters of rope now flexed quietly with the tide. One sailor, after unloading cargo onto a mulberry pontoon during practice operations, described it like this: "The whole thing swayed like a drunk man walking across a field, but it never broke. It moved, settled, moved again. It was strange. So much steel held together by something that came from the hands of a farmer." The War Office began issuing rope production statistics alongside tank and shell output. Weekly reports listed tons of fiber processed, meters completed, reels shipped. Between March and May of 1944, the rope program produced over 1 million feet, nearly 200 miles, of invasion-grade hawser. Each reel was numbered, dated, stamped with inspection codes. They were shipped to assembly points along the southern coast: Southampton, Plymouth, Portsmouth. Loaded aboard transport ships, hidden below decks, they waited to play their part in history. Still, none of this felt heroic. There were no medals for rope makers, no battlefield for rope to charge across. The people who twisted it did their work quietly, often not knowing exactly where their product would end up. But they knew why. Because somewhere out there, across the water, a bridge was going to need to hold. And when that moment came, when the wind howled and the waves tried to tear it all apart, it wouldn't be the tanks or the guns that kept it standing. It would be the line between them, a line made by hand, treated with oil and tar, and tested by the oldest force on Earth, the sea, the bridges that fed an army. At dawn on June 6, 1944, the greatest amphibious invasion in history began. Over 5,000 ships, more than 150,000 men, and hundreds of tanks and vehicles surged toward the beaches of Normandy under gray skies and pounding surf. But Operation Overlord was never just about getting onto the beaches. It was about staying there. The planners knew the real battle would be fought in the days after D-Day, when the beaches turned into bottlenecks and the army began to starve. France had no usable ports. German forces still held Cherbourg, and every harbor within reach was destroyed, mined, or heavily defended. That's why the Mulberry harbors were everything. Each was a floating miracle, a port with no foundation, built from scratch. In the early morning hours of June 7th, a day after the landings, tugs began pulling the first massive caissons toward the coast. These floating concrete blocks, each the size of a small building, were sunk in position to form breakwaters. Behind them, crews assembled floating piers, pontoon roads, and dock platforms. All were carried across the channel in pieces, then bolted and moored on the open water. Mulberry A was built off Omaha Beach for the Americans. Mulberry B, called Port Winston, was built off Arromanches for the British. In less than a week, both were operational. Every day, from June 10th onward, convoys of Liberty ships offloaded tanks, trucks, jeeps, barrels of fuel, artillery pieces, rations, and thousands of men, not onto the beach, but onto floating bridges made of steel and concrete, and held together by rope. From sea to shore, each bridge was tethered at dozens of points, using pairing hawsers, the triple braid, tar-sealed lines made by hand in the rope walks of England. Each line flexed with the tide, stretched with the wind, and returned to shape like a heartbeat. Where steel cables had snapped in early tests, these ropes absorbed the chaos of the channel. British engineers marveled at how the entire structure moved like a living thing, not rigid, but responsive. One officer described it as watching the sea breathe through the bridge. In its first full day of operation, Mulberry B offloaded 2,500 vehicles and 7,000 tons of supplies. By June 25th, that number had tripled. The Allied war machine began to pour through, rations for 500,000 men, barrels of fuel for every tank, spare parts for everything from Sherman tanks to Spitfire wings. And through it all, the bridges held. They held through wind and wave, through night and fog, through the thundering pressure of heavy trucks and tanks rolling across them hour after hour. They held not because they were indestructible, but because they were built to move. Each rope connection acted like a tendon, stretching under pressure and tightening with slack. The bridges didn't resist the sea, they danced with it, like Perring had taught. On June 15th, during a minor squall, a section of bridge at Mulberry A snapped free when a steel anchor chain failed. Just 20 meters down the same span, a rope hawser, untouched, untreated, dismissed by some officers as backup, held. A single rope, looped and knotted by a farmer's method, kept the rest of the floating road from drifting into the surf. By the end of June, both Mulberry harbors had offloaded a combined 500,000 tons of war material. The bridges, anchored by Manila hawsers, had become lifelines, arteries carrying the blood of an army. General Eisenhower later wrote in his memoir, "Had we failed to build and maintain the Mulberries, the invasion would have stalled on the beach. Their quiet success may have been the most important engineering victory of the campaign. And the ropes, those unsung dark lines beneath the platforms, played a hidden but vital role. Soldiers never noticed them. No one saluted them. But every man who drove a jeep or hauled a crate across that floating bridge did so because those ropes held. Even German prisoners captured weeks later were astonished to learn that the Allies had constructed entire ports, seemingly out of thin air. One officer reportedly asked, "You mean your army floats on rope?" A British engineer simply nodded. "It floats on rope that listens to the sea." The night of the storm. The sea had been calm for days. The bridges swayed gently, the tide obedient, the war machine humming. Supplies flowed steadily from ship to shore, tanks, crates, fuel drums, soldiers, hour after hour, around the clock. But on June 19th, 1944, 10 days after the first landing craft touched sand, the weather turned. At first, it seemed like just another channel squall. The skies darkened, the wind picked up. Whitecaps appeared in the distance. Engineers on the floating bridges secured extra lashings. Crews in the harbor checked anchors. But they had no idea what was coming. The storm that hit that evening was the worst in 40 years. Winds reached force 10, over 60 miles per hour. Waves climbed past 15 feet, crashing into the pontoons and caissons like hammers. Rain came sideways, mixed with salt and foam. Visibility dropped to nothing. Commanders couldn't see their own ships. Orders vanished into the wind. At WWII, the American harbor at Omaha, the damage began within the first hour. Concrete caissons tore free from their moorings and smashed into each other. Pontoons twisted, fractured, and capsized. Trucks were thrown sideways. Steel cables snapped like violin strings. By midnight, entire sections of the floating bridge had vanished beneath the surf. Soldiers tried to brace the roads with new steel lines, but it was hopeless. The water was too strong. The steel too brittle. The night too dark. In the storm's eye, one American colonel was heard shouting into the void, "We've built a highway to hell and handed it to the ocean." By morning, WWII was gone. Nothing could be salvaged. The storm had torn it apart, section by section, until nothing remained but broken slabs of concrete and the sound of the waves. But 20 miles east, something else happened. At Arromanches, the British harbor, Mulberry Bee, faced the same storm, the same winds, the same violent waves. But it did not collapse. It bent, it flexed, and somehow it held. Captain Thomas Blake stood at the edge of the main pontoon as the wind howled around him. Rain lashed his coat. He could see the bridge tilting under the weight of each wave, rising and falling in slow motion, like the chest of a drowning man. He watched as the steel chains tightened to their limit, snapped one by one. The sounds came sharp and fast, like rifle shots. Each time, he expected the road to tear free, but it didn't, because something else took the load. The ropes, long, tar-black, hand-twisted ropes, looped and knotted between each segment, stretched, absorbed, and pulled back. Over and over, dozens of them, hundreds, holding the entire floating harbor together like sinews between bones. Blake grabbed one and held it in his hands. It was wet, slick, warm from friction. He could feel it move, tense, relax, like a muscle under stress. He shouted to his sergeant, barely audible through the storm, "It's the ropes. They're saving the damn thing." For 3 straight days, the storm battered the coast, and for 3 straight days, the ropes held. By the time the winds calmed on June 22nd, the numbers told the story. At Omaha, the American harbor had lost over 75% of its infrastructure. It would never be rebuilt. All U.S. supply operations had to be rerouted through British facilities. At Arromanches, Mulberry B survived with just minor damage. And in every post-mortem report, in every engineering debrief, one detail kept resurfacing. The rope moorings outperformed steel. They had allowed the bridges to shift with the storm instead of fighting it. They had taken the load no one thought they could survive. Weeks later, a captured German officer said, during interrogation, "We were told the Americans would be stopped by the sea, but it seems the sea obeyed them." No one told Arthur Perring. Back in Dorset, he was already back in his barn, twisting new coils for fishing nets. He hadn't heard about the storm. He didn't know that his ropes had held when everything else had broken. But Captain Blake never forgot. In his after-action report, he wrote, "We lost concrete, we lost steel. But what held that harbor together was a thing made by hand, soaked in tar, and taught to bend instead of break. A farmer's rope. That's what saved it." And so, the longest floating bridge of the war, 6 kilometers of roads dancing atop the sea, survived not because of brute force, but because of flexibility, foresight, and a lesson passed down by hands that had never worn a uniform. When the war ended, the world looked forward. Victory was claimed by generals, tanks, and strategy. Few remembered the ropes. Mulberry A was destroyed. Mulberry B was dismantled. The floating bridges that fed an army disappeared without ceremony. But the quiet miracle, the handmade rope that held them together, was already forgotten. Arthur Perring returned to his farm in Dorset. He never spoke of his role. When asked what he did during the war, he said, "Tied some lines." He kept a coil of rope on a shelf in his barn, nothing else. But the rope he made had held the invasion together. It had survived the worst storm in 40 years. It had absorbed the fury of the sea when steel had failed. No medals were given. No speeches were made. Yet the lesson lived on. Engineers quietly adopted the principle of flexibility over rigidity. Offshore oil platforms, modern bridges, and naval shock systems began using dynamic mooring, systems that bend, stretch, and recover, instead of snapping. They no longer used hemp or tar. They used nylon, Kevlar, and carbon fiber, but the logic, the humility to let the sea move was the same. At the Royal Engineers Museum, a single section of Perring's rope remains, labeled simply Manila Hawser, Port Winston, 1944. No fanfare, just a thread in history. Arthur Perring died in 1964. No obituaries mentioned the harbor, but the legacy of his rope lived on, not in headlines, but in everything that still holds because it knows how to bend.